Recording is running? Perfect. So, welcome to my talk. What do you think about this piece of code? Do you like it? Do you hate it? Maybe somewhere in between? You can show if you like. So, yeah, I see a trend. Well, let me tell you this. If this code was a gladiator and I was the Roman emperor, it would not be a happy ending. Let me tell you why. This code mixes the core functionality with error handling, making it hard to see what the code actually does at a glance, and it's a lot of repetition. In addition, we have a bool return value that's actually not a return value, but is a success flag. It tells us if the function succeeded, and the actual return value is hidden as a biref bool parameter. We're never going to mix those two up, are we? Take exceptions, and you could have something like this. Except this is not a talk about exceptions. You will have to throw somewhere up in the call stack. You will have to catch somewhere down in the call stack. And if you don't catch, or you don't catch the right type of exception, your application terminates, your customer is angry. And some people can't or won't use exceptions in their code bases for some reason or other. So back to square one. Other ideas? Well, how about this? We have a class and we take a class member and make it an error flag. Isn't that wonderful? Looks pretty. Except we have just shuffled the boilerplate code around. It's now inside the functions, hidden from sight and the slide, but it is there. And woe to us if we forget to check the error flag at the beginning of a function. Anything could happen, really. And congratulations, we have just built our own little dependency hell. Every function now depends on the MB error flag, no matter whether it had anything to do with the others or not. This is called shared mutable state, and it's poison to local reasoning and thread safety. Okay, let's start a bit smaller. Let's fix the return type issue. So instead of having a bool return value and a bool out parameter, we combine those two into an optional of bool. That way we can clearly indicate if we return empty, our function somehow failed. And if we return an optional containing a value, we can read the value and use it. And then we throw out all our if statements and let optional do the work for us. This way, we can cleanly read the sequence of the function. This is a monadic operation in action. My name is Robert Schimkowitsch, and in the next 45 minutes or so, we're going to talk about what monads are, how to use the monadic operations provided in C++23, and maybe we go a bit beyond that. The talk has a lot of examples, but don't worry if you don't catch every detail. There's going to be a link at the end, and behind that link you will find all the examples, source code, further references, articles, videos, whatever you'd like. If you have questions, immediate questions to what I'm talking about or to the slides, please raise your hand. I will try to answer as best as I can. Yes, and there is a microphone, so please wait for the microphone before you ask the question. I would rather keep longer and more tangential questions to the end of the talk, if that's okay with you. All right. Before we talk about monads, we have to talk about functors. Functors are similar to monads, they are related. They are a bit simpler, but they are similar to use. So it's it makes sense to understand functors before we come into monads. Is this a functor? Who says, yes, this is a functor? Who says, no, this is not a functor? Okay, nobody plays along. The problem is you would have won either way because both yes and no is correct. This is something I would call a function object, but some people and some literature does call it a functor, but this is not the functor we're looking for. So what are we looking for? Let's say we have a type x and a type y, and we have a function that we can use to transform x into y. So make it concrete. We have a double, we have a string, and we know how to convert a double to a string. A functor is a wrapper that is able to transform its content if we provide the conversion function. So in our case, if we have a wrapper around double, what can that be? That could be a container, it could be an optional, just to name two examples. We would have a container around double, for example, and we can transform it into a container around string using our conversion function. That's the basic property. In order to be considered a functor, it has to follow two rules. The first rule is if we use an identity function. An identity function is a function we input a value and we get back the same value. It sounds silly, but it actually has its uses. If we use an identity function on a functor, the resulting functor must also be identical, which means we cannot have some side channels and change some state besides. And the second rule is if we have a sequence of transformations, like from x to y to z, it must not matter whether we do this sequence in a functor, x, y to z, or we combine our conversion functions into one function that can directly convert x to z. The result must be identical. But let's look at an example. I have a classic loop here, and we are going to show how to transform it into functor-style code. So I have a vector of doubles, and I prepare a vector of strings for our results. Then we loop our doubles. Okay, what are we going to do here? We square the value, and then we format it as a string using std format as C++20 facility. And then we push it into our result vector. And at the end, we have a vector that contains our squared values as strings. In order to make it a functor-style code, we need to have the conversion functions as callables. And in this case, I just made them into simple free functions. Now, truth to be told, this makes sense also for the classic loop version. So let's refactor the code there. But please note, the classic loop actually invited us to write the code inline, and I've seen loops that have grown and grown and grown and grown because nobody ever thought of refactoring them. The functor leads us in a different direction. But let's look at the function. So first function squares the value. Second function formats as a string. And this is how we will use it in functor-style code. So we have transformations. We have two transformations. And the inner transformation squares the value. The outer transformation then formats it as a string. And then we have an object strings. I will come into that. And if we iterate it or if we draw the values out, we will get the exact same values as before. Is this code readable? Yeah, I think we can improve that. Same code, same logic, different notation. Here we use a pipe operator, and now we can read the sequence left to right, top to bottom, and we don't have to count opening and closing parentheses. How does it work? It basically injects the output of the previous operation into the first parameter of the next operation. So here's a comparison of the two codes. Now, behind the scenes, things work a bit differently. The strings of the functor style code is not a vector, but it is a so-called std ranges view, which means nothing is done in this line of code. It's just a preparation. I just declare what I'm going to do. At this point in code, the strings does not contain any values. What will happen when I start iterating it, it will provide the values on demand. This is called lazy evaluation, and it has some advantages. For example, if I want to run an algorithm until I hit a certain value, and then I want to stop it, of course, with the lazy evaluation, I will only call the conversion functions necessary to get to this point, and then it will stop. There will not be any unnecessary code executed. Also, we can easily work with infinite ranges. Imagine random numbers. We can imagine random numbers as an infinite container or view, and we can easily use this in this kind of notation. There might be some overhead, especially on the memory side. So if you are on embedded and very memory constrained, you might want to benchmark this before using it. And there are traps. Of course there are, it's C++. So who sees the bug? Let me rephrase that. Who can explain what kind of bug we have? And please don't tell me the species. Any suggestions what kind of bug we have here?
The letter transform?
Yeah? Yeah, he should give you the mic, actually. That's the...
The letter transform is like not a functor. It is just a... I'm actually not sure if ranges allow the letter, it doesn't do what you expect it to do. It doesn't take the text of it. You would need a lambda to, or for example, a lambda to get the text out of it.
It compiles.
Yes.
I can assure you of that. It compiles and then it crashes. Why? So we have a sequence, a pipeline of with two steps. And in the first step, we call get nearest entry, which is just a function that returns a struct by value. And then we just want the text, so we just point to the member. And this gives us a reference to the member. But the C entry we got in the first stage of the pipeline is a temporary. It goes away, and we are sitting there with a dangling reference that points to nothing. Dangling references are generally something you can easily get in C++, but if you're not used to this notation, it might be harder for you to spot. And there's one more thing. This is the type of the strings in our functor code, at least for MSVC. It could be slightly different in other compilers. And I call that untypable. So the auto keyword is pretty much the only way to make use of this. This means you cannot separate declaration and definition into different files. So you can either have them both in a source file or both in a header file. And this, what can we do about that? One way is to convert the output of a view into a container. And C++23 gives us a very nice function for that, which is ranges2, std ranges2. And it can convert a view into any compatible container, which is not only the standard containers, but also lots of library containers. For example, I know that Qt containers work with this, just to give you an example. This way we get now a clean return type for our function. We can separate declaration into the header file, definition in a source file, but we lose the lazy evaluation because in that single line of code, everything has to run. The other option is that we return the view. So we return auto. But then we have to either put the function in the source file, and we can only use it inside that source file, or we put it in a header file, and then we have to make it inline so we don't get multiple definition linker errors, because functions returning auto are not considered template functions. Template functions would be inlined implicitly. Non-template functions, we have to write the keyword. When you do this, please keep in mind that the view depends on the lifetime of the data that it uses. So if the data goes away and you still hold the view, yeah, you are in the middle of the ocean with no boat. As you have seen, passing callables is pretty central to using Functor-style code. And when I started this style of coding, I often ran into trouble finding a way to fit the functions I had into the functors that I wanted to use. I wrote complex adapters, and sometimes I just threw my hands up in despair and gave up. I'd like to spare you that. So I will show you the most important ways to feed your functors so that they will thrive and grow. We have already seen the use of free functions. That's pretty simple, as long as the functions don't have any overloads. We will come to handling overloads a bit later. Basically, the same goes for static functions of classes. We just have to add the class name for qualification. It works the same way as a free function. And here comes the Swiss Army knife. Inline lambdas in general, and here an inline lambda, this is a simple and direct way to provide the callable that we need. I would use inline lambdas mainly where we have very short functions, where we have functions that we only want to use a single time and not reuse anywhere else. Where can we use them? For example, they can help us with overloads. Here I have two free functions. One takes a double, one takes an int. And if we just put the function into the transform directly, the compiler will be confused and will tell you so in no uncertain terms. Use it the lambda and it picks the overload and life's good. This is the simplest way I found for picking the correct overload for this kind of problem. Another typical issue, we have a function with multiple parameters, but our functor will only provide one of them. Well, take an inline lambda, pass any extra parameters in the capture list under the square brackets, and keep one parameter that you want to have passed through the pipeline. And then you call the function with the multiple parameters inside the lambda. Using a class member function also requires a bit of work. So here, now it depends, does our functor provide us with the instance, the object instance that we want to call on? Or does it just provide a value that we want to put into as a parameter into a member function? This example, the functor provides the object instance. So we take the object instance as a parameter, and we just call our function on the object instance. If it's the other way, if the functor passes the value, well, we can again pass our object instance by capture list. Here is the conf in the square brackets. And that also works nicely with a lambda. If you want to use a lambda multiple times, or if you just want to give it a nice name to make your pipeline read nicer, you can use a named lambda. And I would actually recommend that for anything longer than one line of code at least. Sometimes I do it for smaller lambdas just to make the pipeline very readable. Function objects also work directly. So if you have a function object, you can just pass it in. And basically, I mean, a lambda and a function object are very closely related, so there's no surprise. There are more options, and I will just show them briefly. I will not go into them. Some of them may make your code shorter, maybe even more readable, but you don't need any of them to make it work. It's just something to look at if you want to go a step further. You will find all this in the material at the end of the talk. Well, another nice thing is if we want to inject behavior. What do I mean? Somebody from the outside should have a way to influence what the pipeline does. I can pass a stud function. A stud function wraps any callable, free function, static function, lambda, whatever, and we can pass it around as a parameter, and then we can pass it into our functor, and it will execute whatever is behind that function. Of course, we can also do that with template parameters. A template parameter can be a function, so we can pass in the template function parameter and pass it on to the functor. If we want to make sure that this is a function of the expected type with the expected parameter, we can restrict our template argument using C++20 concepts. And here I use stud invocable, which means I can call it with these given parameters. We have a question here, please, Mike.
Not really a question, but in case it would be library code, you might as well use invoke result to ensure that the result is non-void.
But can you repeat?
Yes, in case that would be part of a library, you might as well, you could also add a requires to make sure that the return result of the function is non-void.
Okay, so of course this checks only the ingoing parameters. It does not check the return type, yeah. I think I would have to look a bit more closely. Thanks for the input. Now, stud function or templates, well, stud function has a bit of runtime overhead. Templates are, come with the typical complexities of templatized code. So, yeah, it's a trade-off and you have to make the choice. Just to summarize, basically lambdas are your friend in most cases, and they will get the job done in most cases. And if you add stud function to the mix, you have almost complete coverage of all cases that need to be covered. Okay, let's go one step back to summarize. So a functor is a wrapper that can transform its contained value given a conversion function. We should not confuse it with a function object. Functor-style code declares a recipe, a sequence that I want to execute without necessarily executing it right on the spot. It's readable and composable. And as we have just seen, there's just many ways to feed functors, and that also goes for monads, with callables. We have a question.
The functor does not change the outer container, or can it change also the container?
You mean the type of the wrapper?
Yes. Mm-hmm.
So I think that would be something outside of the typical functor specification. So normally, I mean, of course, you can have outside a function that takes one type of functor and returns a different type of functor. But from my understanding, that would be outside of the functor itself.
Okay.
So we have seen what functors are, and we need just one more thing to make them monads. Join. Join is an operation that unwraps one level of nesting. So if we have, let's say, a wrapper a wrapper of string. Through join, we can make it a wrapper of string. Now, how is that useful? In real life, we often have functions that don't just take one value in and output another value, but we have functions that take one value and give us, for example, a container of values. Let's say we split a string. We take one string and we return a vector of strings, for example. Or we call a function with a value and it returns an optional because it might fail. And these are basically wrappers. If I now call such functions in sequence, I get wrappers of wrappers of wrappers of wrappers. And join helps me to keep that to a manageable level. But let's leave theory aside and look at examples. It has been said that a compiler is a tool that takes files as input and returns diagnostics as output. Let's forget for now that it also might produce usable object code, and let's focus on the diagnostics. We want to get the diagnostics and we want to print them. And for that, I have a function that will print a single diagnostic. Then, of course, I have a function that will compile a file, and it will give us a vector of diagnostics. And of course, just compiling one file is usually boring, so I made a function that will take a project and will grab all the files in that project, and it returns a vector of files. And let's look at the classic implementation first. So we have a loop over the projects, and then we get all the files in that project, in one single project. We loop over all that files. We compile a single file. Then we loop over the diagnostics, and we print a single diagnostic. Who uses code like this? Yeah, I would say clear majority. That's the monadic style. Let's walk through it. We start with the project, and then we transform it into files using the get files in project. Get files in project. So now we have a vector of files. So we join, making it just a vector of files. Then we compile, which gives us a vector of diagnostics. So we join again, giving us just a vector of diagnostics, and then we can just loop and print. So here are the versions side by side. Do they behave differently? Well, in effect, no, because they call the same functions in the same order with the same parameters, collecting the same results. So I would consider that equal behavior. That said, there could be surprises, especially if you start using more complex functions in the std ranges library. Fortunately, there's an antidote. And the antidote is, don't use functions with side effects. What do I mean by that? This is a really nice function. It has two input parameters. It returns an output parameter, and that's it. I can look at it in isolation and understand what it does, and I'm not going to be surprised if I call it 5 times or 100 times. I think most of us hopefully know that global variables are something to be looked at carefully. But in my view, that especially when you use it in functors or in monads, please also avoid changing member variables. You will sometimes be surprised how often, for example, your function is called. So this goes especially for std ranges views, but it's generally good advice for functors, for monads, in my view also in general. Now, in our last example, we have conveniently assumed that our functions don't fail. And if they do, they still return usable results like an empty vector. we have a question here.
The join only removes one.
One level of nesting.
So if you have a wrapper of something, we get a wrapper of something.
Yes. So you would have to call it as many times as you need. But typically, yeah, you do an operation, it adds a layer, and then you remove that layer.
And if I have a wrapper of something, I get a wrapper of something.
That depends on the specific monad if that is even possible or not. All right, so we had code that actually did not fail, but in reality, we often have functions that fail in some way or other. So let's have some fun with failure. And I jump right into the example. So let's say we have a database or a storage structure or something, and it contains very different kinds of data, like trends, images, and tables. And let's look more closely at the table. We can identify a column by key or index, and we can identify a row in the same way, which gives us a cell. And now we can query, does the cell contain a number, numeric value? And if it does, we can check if it's negative. So let's say that's what we need. We need to find all the places where we had a negative profit or something like that. And let's make a function that helps us do that. I call it getNumeric table value negative. This is our goal. And what could possibly go wrong? Well, the key could be invalid. It might not be a table. Maybe the cell location is out of bounds, and the content might not be a number. Then we have one stage which does not fail, at least not for the integer types we are using. And this would be the functions we use for a classic implementation. So we start with getElement. We pass a database, I call it DB here, and a key, and we receive an element as a by ref out parameter. In addition, we receive a bool return, which indicates success, true, or error, failure. I've seen these a lot in old code, and I hate them because they don't compose, and they are often not as efficient as possible. But that's we have in existing code, so let's take a look. But basically, the pattern repeats. We get a table based on the element. We get a cell based on the table and the location. And then when we have a cell, we can try to extract a numeric value from it. And now this is the code. Who has a flashback here? Yeah, we have seen this code before. So let's take a look. We create an element on the stack. We call getElement. It will fill the element if possible. If not, it will return false, and we ourselves return false. And then we repeat and repeat and repeat. And finally, we can check if the value is negative and return true. Success. Yeah! If you want to use it in monadic style, I would change the function signature. So we combine the bool success flag and the actual return value into an optional of the return value. So if the function now fails, I just return an empty optional. And if it succeeds, I return an element. And the same goes for getTable, getCell, getNumeric cell value. Now, for the sake of completeness, I've added an isNegative, which, of course, is not strictly necessary. Could be just an inline lambda, for example. But it's interesting because the function itself does not fail. And because of that, we do not return an optional automatically here. We do return just a bool. OK, and then we start a chain, our pipeline, and we start with getElement. So the element is now an optional of element, and we can call our next function conditionally. That is, getTable will only be called if the element has a value, if the optional behind it has a value. So that means we pass our next operation as a parameter to end then. If the optional does not contain a value, it will short circuit and it will just go to the next stage on the pipeline. And it will basically go all the way through, and at the end we stand with an empty optional. Since we are working with values that may be there, it's also called the maybe monad. Quiz time. We don't see any join here. Why do I call this a monad? We have...
I guess because it unpacks the value of the optional, and in case it's there, it uses that value to pass on to the next callable, and in case it isn't there, it returns the actual null opt in this case.
Okay, so yes, good answer. So getElement returns a std optional. But getTable, the next function, does not need an optional, it takes just an element. So we have successfully unwrapped one level of nesting, like a good monad should. Now, look at another example. Let's say we have an int and we have an optional of int. How would we just unwrap one level of nesting? Does somebody have a suggestion for that?
Join?
There's no join in optional. You can solve it with the tools we have already seen.
You could use .value or .value or. If you want to have a fallback.
But you know something that's not been on the slide. It's a correct answer, but I will show you a different one. Remember this rule? Identity function, functor does not change. We can make use of that. We can call end then with an identity function, which will unwrap one level of nesting and then do nothing. So it's basically just a join. It's for the quiz, it's not for real code. But I think it helps to understand how these things work together. At least I hope it does. Okay, in the next stage, we need to pass an extra parameter. So we do that by lambda, like we've seen before. And then we call the and then, yes, literally we call the getNumeric cell value. Now the last line is special because here the function is negative, returns a bool and not an optional. So actually what we want is, we want to just transform the value inside the optional from, in this case, int to bool. So it's also called transform like in the ranges. It will also only execute if the optional has a value. So what can you do with a std optional that you get as a result of that whole function? Well, yeah, we have a question here, maybe to that slide.
Why can't we use end then also in the last line?
Because it will try, basically end then expects that the function will return an optional of some kind, the end then. I'm not sure if it would compile even. I'd have to try that. It's just wrong. But I'd have to check what it does, and I don't want to take the time now to start the IDE and try it out live. So we can try it after the talk and see what the compiler, which finger the compiler shows us, so to speak. So what can we do with optional? Well, we can check if it has a value. And if it has a value, we can get the value. If we try to get a value from an empty optional, we raise an exception. Well, optional does. And yeah, we have the code comparison. Now, let's have a little poll. Who prefers the classic version of code? It's actually less than in my company. And who prefers the monadic version of code?
I have the feeling that the classical version could be improved
Yes.
with ORs. So if you put all the declarations on top and then say get element or get table or get cell or and so on, it would be shorter, and I think it could work.
You might have allocate all of the elements in that case, which might be expensive. But it depends.
Yeah, it certainly, yes. I mean, this is basically the kind of code I see that I see in production code. I'm not a fan of very complex and long if statements because you need very good indentation to make them really readable, but it's entirely possible that you can make much nicer code, I admit. Of course, I didn't want to push the classic version too much, so I have to admit. So now, okay, we have our function, and okay, we have a question here.
My question is, what version of the code is easier to debug? Well, in the classic version, you clearly can place a breakpoint and see where it triggers, but for example, if one of the constructors throws an exception, where do you catch in the debugger that exception in this notation? So
yeah, that's true. The classic version is easy to debug. Where can you debug the monadic version? Well, you can set breakpoints, of course, in all the callables that you provide. But they might be called a lot later than you expect, of course. In case of the ranges view, for example, here it's a bit different. I think this is not lazy. This is going to evaluate directly. You wanted to comment?
If you got some spare time on your hands and just can create a quick lambda, you could also make a lambda which wraps all the callables and then, for example, logs it. Or you can also place a breakpoint in there so that you don't have to place breakpoints in all of the other functions. So you just have one breakpoint and not like 10.
Okay. I mean, these concepts are still rather new to C++, although they have existed in other languages for quite some time. So I feel that there is still a lot of potential for tooling, for IDEs, for debuggers to catch up and also give us more help in debugging this kind of code. Then again, from my experience, you get a lot more compiler errors than runtime errors in this kind of code. So you will spend more time until the code actually compiles. But when it does, it's rarer that it will have errors at runtime. At least not in the structural part of the code, maybe inside one of the functions. And inside one of the functions, you can easily debug again. So it's true, you need to relearn some things, and probably the tooling has to improve on that front as well. So, okay, we have our function, but what about, what if we have an error and we want to log it, and so what do we do? Now, and then has a nice sibling, which is called or else, and it allows us to catch an empty optional and do something with it. And in this case, I want to log. Now, why is this a template function? The log function now should return the same type as before, so we can just pass through without changing anything. And for that, it needs to know the return type that we want. And that's just a little trick to make it generally usable. If you know exactly what you want to do there and you know the type, you can just write a non-template function as well. Now, what can the log function do? Well, for one thing, it can print out that an error happened. Hooray. For that, I use another C++23 facility, std.println, which prints by default to the standard output with a line break. The std print and format family of function is safer than the old printf, and more performant compared to Stream.io. Maybe not as performant as format library, but certainly more performant than the Stream.io. I've seen some benchmarks for that. But that's a topic for a separate talk, or several talks, actually. Now, in the next line, I capture a call stack. That's another new facility in C++23. So stack trace current gives me a dump of the current call stack. And inside that, I get one entry per level in my call stack, from the top, where I'm right now, until the bottom to the main, or below even to the operating system. And in each of these entries, I get a source file, I get line, and I get a description. And without going into further details, yes, please, I have another question.
Do you have benchmarks about stack trace?
No, but what I know is that it does not need to do, basically you do not have to opt into it, which to me sounds like a zero cost overhead abstraction, because actually we need all the information anyway. Basically, in order to return to our calling function and so on, we need all the information anyway. I mean, what I mean with that, as long as you don't call std stack trace current, you have no performance issues at all. I do not know how fast it is to capture the call stack. But typically, it's not something I would imagine doing too often.
What about the source file and source line information? Isn't this available if debugging information is missing?
Well, but how do you get it from inside the code? If you are in a debugger, well, you can see it, of course.
Yes, but if you compile without debugging information, the code has no information about source files
I think
and
then
source and so on.
You will just get a list of addresses, basically. Yes,
okay.
Probably. Yeah, well, I compile typically in release with debug information.
Yeah, sure, but actually, like, source location works. I'm not sure if that.
Well, no, that's something different, because source location.
Yeah, source location is something different, but doesn't stack trace, at least for the first entry, fall back to source location?
That would be an implementation detail. I would have to, basically the source location is evaluated at compile time. So whatever I have release mode or whatever, it will basically just literally say the file name when it's compiled. Std stack trace, it cannot preventively go through the call stack and annotate everything. So I think it will be tied to the debug. But this is not a talk about std stack trace, so I did not dive that deep. There is a video about std stack trace, just about std stack trace in the material. So if you want to investigate, please do. Well, finally, we can return a value. And I can choose to return null, what we got. I can also provide a fallback value. So that gives us an interesting option of first failing, logging failure, and then finally still providing a valid fallback value. There's one problem, however. We will not capture the right error location. So imagine we have a problem in getCell. Let's say the cell location is out of bounds or something like that. This is our error location. When we come down to the log function, it will capture the call stack of the log function. And that's just no good. So we need something better. Std expected is a C++23 addition. It's very similar to std optional. So let's just change our functions to return std expected. The first template parameter is the value as with std optional. And the second template parameter is error information. And here I just created a custom class called CR, which can contain error information. Now, if a function fails, it does not return empty, it returns an unexpected. And inside the unexpected, I can provide information like an error message, and CR can just as well capture the call stack in its constructor, for example. Then I have the call stack of the true error location. If everything's all right, I just return my value as before. Now the chain of operations is completely identical, except that the log function now receives the error information as parameter. When getCell now fails, we get a CR object with call stack information, error message. It will be sent down to the log function. And inside the log function, I can use this information to improve my logging. I can again choose to pass through the unexpected value. I could amend the error information if, for example, I have more context information in this location here. Or I can again choose to return a fallback value. Expected is very similar to use compared to optional. I can check if it has a value. I can get the value. And now I can alternatively get an error. Expected always contains either a value or an error. We've now seen ways to call a sequence of functions, each of which might fail. Sometimes we want the exact opposite. We want to call a sequence of functions until one of them succeeds. And this is easy to do with optional. Let's say I have an application and I want to determine the startup UI language. And I have given the user multiple ways to provide it. Could come from the command line, could come from the registry, if we are on Windows or something similar, and could come from an environment variable. And if everything else fails, I want to provide a fallback language. And this is how we do it. I get the language from the command line, and if the optional is empty now, the next function will be called, or else get language from registry, or else get language from environment variable. And if everything fails and I end up with an empty optional, and now we come to your value or, then I can default to the fallback language. This is just a table. I will just show it briefly. It's in the material. If you want to know which of the features I mentioned your compiler supports, you will see this with a minimum compiler version and so on and so forth. Please look in the material if you're interested. René, I'm a bit over time, mostly due to questions. I have a bit, let's say, 10 to 15 minutes left. I'm fine with that. Yeah, is everybody fine with that? Okay, so let's leave the comfortable path of monadic operations provided with the language and go a bit further. We've seen optional, and there's something pretty similar conceptually, a pointer. It can be a point to an address, or it can be null. So let's write a pointer monad. Who has ever written a tree-like structure using pointers? Fewer people than I thought. Well, I've made a very simple implementation, and in my implementation, a node can contain either a value, a string, or it can be empty. And what I want to do now is I want to find a sibling by key. And for that, I have to go to my parent, if I have one. And then I find my sibling, if the key is valid. And then I want to square the value. Silly example, but it shows what we need to show. Of course, on the way, we could have some invalid pointers. And this is my primitive implementation of the node. On top, I use std variant for the content, so it can be either empty, int, or string. Then I have an interface to get a parent and to get a child by key. Also have an interface to get and set the content. And of course, we would need something to set the parent, add a child, or something like that. Assume it's there, we don't need it for this example. And this is a classic way to implement this. At least I return optional, so I learned something. But before that, I have 2 pointer checks here. And I have another pointer check inside that function because the sibling could be a null pointer. And finally, if I make it to the last line, then I can just use optionals transform. And that's the monadic way. Looks a bit like optional, doesn't it? So there's 2 details I want to point out. The first one, this is inherently safer than the classic version. Ever so often, somebody forgets the manual pointer check. I've been there, I've seen it, I've crashed. Here, you cannot forget the pointer check because it's part of the wrapper and it's just built in. And the second, this is actually a very nice use case for std_memfn, which I just mentioned briefly. So if you think this code is not readable enough, then look into std_memfn. For member functions which have no parameters, it's pretty perfect. Okay, even the get node numeric value got simpler because now we get a pre-checked reference instead of a pointer. So what do we need to do to make this happen? The first thing is we need a template class. Why a template class? Because we want to cater to all types of pointers. But we only want to accept pointers, so we constrain our template argument using std is pointer. And then let's come to the declarations. We have a default constructor which just creates a null object and a custom constructor where I can just put in a pointer. And this pointer goes to my member variable, mptr. Then I have some operators. They give me pointer-like behavior, like I can use an arrow operator. I can say if in brackets to check if the pointer is valid. So that's just a basic set. We can add more. It basically just passes through my pointer member in this simple implementation. And now comes the fun part, the end then. So we have to pass a function, a callable, and I do that by template argument. And the return type is also because we will have to determine it based on what the callable gives us. And in the implementation, we start by specifying our template arguments. tptr is the class template argument, and tcall is the function template argument, the callable. Now, inside the function, I first create 2 helper types. tref is the equivalent reference type to the pointer type. We want to pass a reference to our callable, so I need the reference type. And the second type is the return type, ret, which I can get by std invoke result t. This gives me the return type of a function. As you can see, here I will pass the reference. Now we have 2 branches. And I branch using if const expr, which means that this if statement will be evaluated at compile time. The compiler will only include the block on top or the block on bottom, but never both. At runtime, there is no if statement anymore. The first block is for functions that return a pointer type. And inside I check if the pointer is valid. And if it is, I invoke the callable. Of course, I have to pass it. And I pass my dereferenced pointer. Because I call a function that returns a pointer, I will wrap it into CPTR directly, which allows the user to call the next and then directly. If my own pointer is empty, I also return a null pointer, but of the correct type. So I change the pointer types, but it's still a null pointer. The second branch is for functions returning not pointers, and at the moment I only accept optionals. Could be extended. So first I create a type alias for the value inside that optional, and I check if it is really an optional, so the user gets a nicer error message. And then, if my pointer is valid, again, I invoke the function, and this time I don't do any wrapping, I just pass the optional as it is. If my pointer is invalid, I return an empty optional, default constructed. Here are the differences between the two branches. Wrap pointers into CPTR and leave non-pointers as they are. So on the calling side, I need to opt into the monadic interface by wrapping my first pointer into CPTR. And then the rest is automatic, basically. I just get a CPTR after CPTR, and I can always call and then. But the transform on bottom is optionals transform. So I can actually seamlessly transition from a pointer monad to an optional monad. And it's pretty nice to combine those two. Of course, this is just a sketch, and there's a lot that could be added to make it, let's say, production ready. But if you happen to have a code base with lots and lots of pointers flying around, it might be a way to make it safer and more usable. As a takeaway, it's not magic to write monads. It doesn't even take a lot of code, but it's typically template code, so the general advice for writing templated code applies. We have seen some examples, but we've actually only seen 3 use cases. I'd like to very briefly show you 3 more, so you have a broader idea of how you can use monads. And the first one is the continuation monad. Here, the wrapper wraps a value that does not exist yet. It will appear at some point in the future. And when it does, we want to call our next operation in the chain, and then the next, and so on. The continuation monad makes it really nice to chain asynchronous operations, because it basically comes down to do this operation, then do this operation, then do this operation, and it just works. Not yet in C++, but there are libraries, and it might be coming. Yes?
Isn't this a promise? In
value,
Java, in many languages, there is the concept of a promise, and this sounds like a promise.
It's I know the pair of future and promise. One is basically the one that's inside, and one is the one that's outside, that's basically controlling the flow.
So this is not a promise?
The value inside, I would call this wrapper a future, because like on the stock market, the future is something that will be realized at some point in the future. But to my understanding, a future always has a promise connected to it, because it's a promise that the future will appear. And the promise is the part that allows you to control basically, for example, to cancel the operation and things like that. But there might be, let's say, naming tweaks, but I'm pretty sure it's the same concept behind.
Okay.
The next one is the state monad. And here the wrapper carries extra state information that can be injected directly into every function that it calls, which means that we are not depending on shared state between multiple chains of calls. We can insulate them completely and make them completely thread safe and independent from one another. And the last one I want to show is the writer monad, which is a bit similar to the state monad because it carries log information. So the function, in addition to giving a return type, also can provide log information. And this log information will be stored and transferred inside the wrapper, which also means that it's completely insulated from any other things that happen in your application and can run in parallel without any trouble and any race conditions. But we have actually only seen the tip of the iceberg. Monads are incredibly flexible. They give you a lot of variation points that you can use to build more powerful abstractions and reduce duplications in your code. It's not that hard to write a monad, but it takes some careful considerations. So if you are new to these concepts, I would recommend that you start slowly, build some experience before rolling them out into your code base. And the best way and the easiest way to do this is to use the monads provided with the language, like the ranges monad, which allows you to chain 1 to n operations using transform and join, like the optionals maybe monad, which allows you to call a chain of functions and which short circuits if any of them fails. The closely related expected monad, which adds error information. And the optionals default monad, which lets you pick first success from a chain of functions. This is the place to start. These are the monadic operations in C++ 23. And as promised, here is the link. I'm sure we will share it also on the website and so on. And I'm not sure if we have time for more questions. Let's say 5 more minutes or so.
In Java, there are streams. And all what you explained now is, for me, similar to the streams. Have you compared the monad concept of C++ with the streams of Java, Kotlin, and all these other languages?
I admit I did not look into other languages, but I know that these concepts have been implemented in lots of languages. So for me, it's no surprise at all that we would find similar concepts in different languages. And there are a lot of languages which had these concepts a lot earlier than C++.
So for me, in Java, they don't use the word monad for that.
Yeah.
It's just streams, and you can apply several things like you did.
Yeah.
And there is an ORLs and so on. And there is also compression, so you can have pipeline and for integer, and you can say, okay, now summarize to something which I did not see in your
the word monad comes from the theory behind the category theory. And I mean, of course, it's not used everywhere.
I believe not everybody have access to work in the 23rd standard. I believe a lot of people work in the 17th standard, or at least that's what I'm seeing on vacancies. So are there access to monads? Well, maybe not through std optional, but maybe through libraries where this is implemented, or would you recommend to implement of something own?
I admit I have not researched into that. And now that you ask the question, I think I should have. Off the top of my head, I know that there's like a ranges v3 library, which would be even more powerful than the ranges and views that C++ offers. I'm sure there have been other implementations of optionals and that like. I know because I wrote one myself, but it's unfortunately, I cannot open source it, and it's too old anyway. So I'm sure you will find things like ranges optional and expected as libraries, but I have not made a research of that. Can you? We have maybe an answer. Is it an answer to that question? Yes? Or you have a suggestion for a library?
As you suggested, ranges v3, I think ranges v3 is also what, like the author is also who proposed ranges for C++. Yeah. So the ranges implementation in C++ is based kind of based on ranges v3. Mm-hmm. So, yeah.
But then the ranges with v3 is a library.
Yeah, but the question is with which C++ standard it can compile. As far as I know, ranges start with C++ 20.
Not
17? Okay.
17 for sure.
Cool. But there has been a question over... We will look it up afterwards directly.
Yes. I can actually also amend things to the page. So if you have more inputs, more links, please send them to our email address, and I can add it to the page so that we have a nice collection, for example, also of replacement libraries. Yes?
When you chain together expected, do they all need to have the same error, class, or type?
Let me think, how would that work? Yeah, the problem is, when you call and then on expected, and it short circuits because the expected holds the error, you have no way to provide a function that will transform one error to the other. I haven't tried playing around. Maybe there's ways that it could work if the types are implicitly convertible between one another, but that sounds a bit tricky. So as a, let's say, application developer, my approach would be to settle on one kind of error information for at least one part of the code base, if not for the whole code base, and go with that. Mm-hmm. As they say, there's many things you can do, but it's not always smart to do everything that can be done.
Yeah, I'm trying to compare it in my head to exceptions.
Mm-hmm. Yeah, there you have a rich type hierarchy that you can use. That's true. But you could possibly use a type erased class, and then the internals could be changed. So basically, the throwing function could determine what to put into the type erasure wrapper. For the expected, it would look the same, but behind it would have a different object type. That's entirely possible.
Thank you.
Okay. Is there one last question?
Generally, most projects out there are no greenfield projects, and they legacy code, often with side effect. What would be your approach to start a more to move more functional, monadic way of programming? How would you refactor or start refactoring stuff? Because that's generally the problem I see with.
That's my daily work.
Yeah.
Because I have this legacy code, and I try to write in this style, and sometimes you just have to admit that it does not make sense to change a huge function completely because you want to change a tiny bit of code to use Monadic. I've seen it with a colleague last week. He tried after this talk to apply it to his code, and it was just ugly. It worked, but it was really ugly. And I recommended that he reverts to the original version in this case, because you depend that the functions you use have a certain notation form. So basically you have to create bubbles, and in those bubbles you can work with this. For example, I had one class and it did not work correctly. So basically it had an outside interface that was unchanged. And then I just threw away the whole class and wrote a new one based on these principles. And something like this can be done.
Okay, thank you.
So I would say not one line at a time, but one class at a time. You can replace it. Okay, thank you very much. And René, have you...